Hello, young physicist. This is our last video for our unit on energy, and it's about machines. There are a couple skills that I want you to have by the time you finish watching this video. I want you to be able to name and describe some simple machines, mostly levers, pulleys, and inclined planes. I want you to be able to determine something called the mechanical advantage of a simple machine, and we'll do some examples of that. And then finally, I want you to calculate the force required to move something with some different types of simple machines. Let's jump right in. So, in physics, what we call a machine is something that transfers energy from one place to another, or transforms energy from one form to another. We gave a very similar definition for what work is. We said that work could transfer energy from one thing to another, one object to another, and that work can convert energy from one form to another. So a machine is something that does work. Now you may think of a machine as something like this. Something very complicated. Here's a classic example of a type of machine called a Rube Goldberg machine, after the artist that drew them. And he drew these very elaborate machines to do very simple things. For example, here's an alarm clock where there's a bird that grabs a worm and then that fires a gun and hits this balloon and so on and so on. And here's an example of a submarine. But we're not going to be talking about machines like that. Instead, we're going to be talking about simple machines. And there are 6 types. The 6 types of simple machines are levers, inclined planes, pulleys, wheels and axles, screws, and wedges. And what we're going to be concerned about in this course are levers, and here's an example right here, shown to move a boulder, inclined planes, or ramps, and pulleys. And we worked with inclined planes in labs in this unit, and also we've worked with pulleys several times throughout the year. We're going to do another lab with pulleys sometime later on this week. Now we said that machines work by transferring energy from one place to another, or by transforming energy from one form to another, but I want to go into a little bit more detail. So what they're actually doing in terms of physics is they're creating a greater output force compared to the input force. So what you're doing is you're using less force to do the same amount of work. Now usually what happens is, since you're doing a smaller force, it's going to require doing that force over a greater distance. So the amount of work that you do with a machine is the same as the amount of work you do without the machine, except it's going to require less force. So if the work with the machine is the same as the work without the machine, if you didn't have a machine, you'd require this great amount of force, but the distance would be less. Just like lifting up this block right onto the top of this ramp at 3 meters. 3 meters is a smallish distance, but it would require a lot of force. Instead, you could use this machine, an inclined plane, to do work with the machine, and that would require less force, but you'd need to move it a longer distance, in this case 6 meters instead of 3 meters. So even though the force is the output force is greater compared to the input force, you can't put out more energy than is being put in. What machines do is kind of multiply forces, but remember, according to the law of conservation of energy, energy can't be created or destroyed. When we describe how machines help us, we're going to use the term called mechanical advantage. And what mechanical advantage is it describes how the machine changes the work. Mathematically, you can figure this out, and sorry about the formatting here. You can figure it out by dividing the output force over the input force. Or you can figure out mechanical advantage by dividing the input distance over the output distance. And that's kind of hard to understand until you see it in action. So let's see it in action. So I've copied over the formulas from the last slide onto this slide, and I want to figure out the mechanical advantage of an inclined plane. Now what we can do, we have two options: the output force over the input force, which we don't have any information about here, or we can look at the input force, or the input distance over the output distance, which is what we have here. So in this case, our input distance is the 6 meters to push up the inclined plane. And the output distance that we get is 3 meters. So if we take 6 meters and divide it by 3 meters, that's pretty easy to do. That's going to be 2. What are the units for mechanical advantage? There are none, because these meters cancel each other out. Now the cool thing you can do with mechanical advantage is figure out how much force it's going to take to push this block of ice up here. And how you do that is you take this 2 and you use it for the other formula. So let's suppose that this block of ice weighed 10 newtons. Well, to lift that up 3 meters, that would require you to use 10 newtons. Right? You'd have to counteract the force of gravity on that block of ice. Now, if you have a mechanical advantage of 2, the output force is 10 newtons, and the input force is, we don't know. So this is how much force you're pushing the block of ice up the inclined plane. If you shuffle around the numbers, you'll see that 2x equals 10, or x equals 5 newtons. So to get this block of ice up to this point, you could either use less force of 5 newtons and push it a longer distance of 6 meters, or move the block of ice less distance, 3 meters, but use a greater force. Let's look at another example with a different type of machine. Here's an example of a lever. So all a lever is it's a bar that turns on a fulcrum, or a pivot point. And a lot of times that pivot point isn't right in the middle, because if you don't put it in the middle, then you're creating a greater mechanical advantage. So what happens is you push with a smaller force but over a greater distance to move this heavy load a small distance, but it's generating a great force. Let's see how mechanical advantage works for levers. So here's another example of a lever, but the same concept, and we've got some numbers in there. So we've got 2 ways to figure out mechanical advantage, and all of the numbers that we need are here to do both. Let's try the one with how far the lever is being moved. So the lever's being moved 1 meter. That's the input distance. So we have 1 meter. I'm using this formula right here. We have 1 meter as the as the input distance, and the output distance is 1/8 of a meter. And if you do this division, it's the same as multiplying by the reciprocal, or 8/1, and that gives us a mechanical advantage of 8. So what this means is your input force only has to be 1/8 of the output force. Since the numbers are here, let's try it. So now I'm using this formula. In this case, the output force is 80 newtons, and the input force is 10 newtons. If you divide that up, that gives you a mechanical advantage of 8. What this means is that no matter what load is put on this lever, it's going to take 8 times less force to move that load. Let's use our mechanical advantage to try another example. What if you were using this same lever, but now you were lifting a 40 Newton block with it? How much force would it take? Well, we would use this formula. We know that our mechanical advantage is 8, so we'd put 8, and we want to know what's the input force. We know that the output force is 40 newtons. So by shuffling this around and multiplying both sides by x, we get 8x equals 40 newtons. or X equals 5 newtons. So it would take an input force of only 5 newtons to move a 40 newton block with this lever. Let's try this other example with a different. So here, what's the mechanical advantage? Well, let's check it out. It gives us a lot of information. It doesn't give us anything about the distance, so we're not going to use that one. Instead, we'll use this formula. Mechanical advantage equals output force, 30 newtons, divided by input force, 10 newtons. And the answer is right here, so that's a good clue. 30 over 10 equals 3. So what can we do with that? Well, now let's suppose we had a different. How much force would it take to lift a 40 newton block? We said the mechanical advantage is 3. And we want an output force of 40 newtons, but we want to know how much input force, how much effort force would be needed to move a 40 newton object. Shuffling around the numbers by multiplying both sides by x, we get 3x equals 40. And if you divide 40 by 3, what you'll get is 13.3 repeating newtons. Do you see the advantage of using a machine? Less force. The last type of machine we want to talk about is a pulley. And how a pulley works is a lot of times it changes the direction of a force. And it relies on a wheel, like this, that spins on a fixed axis, right here. Now, a cool thing that we're going to learn about in this unit is how you can put a whole bunch of pulleys together. So here's a single pulley, like what we've been working with, and here's a double pulley, where you'd be pulling this way, and the rope wraps around multiple pulleys. Let's see how this works in terms of mechanical advantage and in terms of using less force. To determine the mechanical advantage of pulleys, what you have to do is just count the strands of rope that are supporting the load. So here's the load, and there's just one strand of rope supporting it. This other strand is being pulled, so you don't want to count that one. So this has a mechanical advantage of 1. Here, this is the one being pulled, so don't count it. This is supporting the load, and this strand is supporting the load. So that mechanical advantage is 2. What that means is it would take half the force to lift this weight. In this case, we've got this string supporting the load, this string supporting the load, and this string supporting the load, giving us a mechanical advantage of 3. So what does this mean? Well, let's suppose that this weight was 24 newtons. We could determine the input force needed to lift that 24 newton load. With a mechanical advantage of 1 on this pulley, we'd have our formula of output force, 24 newtons, over input force. Shuffling some numbers around, we'd see that our input force is 24 newtons. In the case of this one, we have a mechanical advantage of 2. Moving some things around, 2x equals 24 newtons, or the amount of input force is only 12 newtons. So you need half the force to move that mass with this double pulley. Now we've got a triple pulley with 3 strands supporting the load, so our mechanical advantage is 3. We're trying to lift a 24 newton load, and we need to know what's our input force. Multiply both sides by x. You get 3x equals 24, or x, the input force, is equal to 8 newtons. So that's all I want to talk about today. Now you're going to get the opportunity to practice this doing a problem set with a partner.